Welcome to Renal Service Staff Annual Review Water for Dialysis. CMS establishes regulations for the use of water and dialysate quality in a dialysis setting. RD 52 2004 is the reference used for CMS as the basis for their regulations. In previous writing of the regulations of the April 15, 2008 publication, prior to that year, there were only 8 tags or 8 regulations governing the use of water and dialysate quality for dialysis use. With the current regulations, there's over 102 regulations that's specific for dialysis. The reason for the increase in regulations is that there were changes in technology, water treatment became more complex, dialysis equipment became more complex, and also too, 1970s there were few technicians, and the regulations were silent as about regarding the competency of individuals in these areas. 2008, technicians provide most of the direct care, and public demanded regulations be put in place. There are 4 questions that has to be satisfied or answered in regards to water analysis. What does it do? How often is it monitored? How would failure affect the patient? And what do I do if it fails? Water comes from 2 different sources, groundwater or surface water. Groundwater is actually surface water that has perked down through the different layers of the ground. In its migration through the surface or through the ground, the water is naturally filtered, and it's filtered in organic materials such as bacteria, um, pollution runoffs, things like that are actually filtered by the ground before it gets to the water table. But in this migration through the earth, it does pick up a lot of inorganic materials such as calcium, magnesium, iron, zinc, copper, sodium, aluminum. So any mineral that the water comes in contact with will change it, as opposed to the surface water. Water on or close to the surface of the land, such as rivers and lakes and ponds, do not have the natural filtering effect of the earth. So it will be low in minerals, but it'll be high in organic materials such as silt, bacterial levels, industrial waste, automotive byproducts, anything that is dumped into water that can actually flow through the surface water. And also the rural area water is also affected by animal waste, fertilizers, and pesticides. So as you can see, the 2 different types of sources of water gives you 2 different types of contaminants that would be subjected to that source water. There are a number of components within the dialysis setting, but not all components are in every facility. Again, because of the different source water, that would indicate what type of pretreatment system would be required for that setting. Do you need to remove organics, or do you need to remove inorganics? So it depends on your source water, and knowing the source water is critical in designing a system. There are commonalities or consistent components used for every facility. The backflow preventer is a typical component and is required in every facility. A softener may not be. Carbon tanks are required for every facility. A pre-filter is definitely required, and we'll go through this as the lecture goes on. The RO system, the DI system are your primary purification process. Ultrafilters, UV irradiators, point of use ultrafilters are also typical components in the system. One of the things that's included in the regulations is V696. Technicians who perform monitoring and testing of the water treatment system must complete a training program approved by the medical director and the governing board. And the interpretive guidance for that is that any staff member who operates the water treatment system must complete a training program. Also, too, in V260, a training program that includes quality testing, the risk and hazards of improperly prepared concentrates, and bacterial issues is mandatory. And the operators of the water and dialysate system equipment system has to comply with the regulations, and audits should be done at least annually. even though you're not intimately involved in water testing, each caregiver is intimately involved with dialysate systems. So one of the things and one of the requirements is for every individual that does dialysis be audited at least annually, and that's what these competency annual competency is for. The difference between normal subjects and hemodialysis patient are included in this chart. As you can see, the normal subject is exposed to 14 liters of water per week, where that calculation comes from the 2 liters a day consumption that is normally what each individual should have. And in a hemo patient is 360 liters per week. That is calculated from the dialysate flow and the typical number of hours dialysis is on. So 500 cc's per minute times 3 hours gives you about 360 liters per week exposure. And also too, the mechanism of exposure is with the normal subject selective across the walls of the GI tract. Selective means that things that the body wants to reject, it will reject and not allow to be absorbed. And non-selective in the patient through the dialyzer means whatever is in the water will go through that membrane. So it doesn't reject anything. Anything in the water will go through the membrane directly into the patient. And of course, normal subject, it's excreted by the kidneys, the contaminants that you drink. And the hemo patient, no kidney excretion. These are partial lists of disasters that have occurred with water. For alumina, for example, dialysis, encephalopathy syndrome, bone disease, and anemia. These are actual events that have occurred. Chloramines produces hemolysis. Fluoride intoxication causes fatal arrhythmias. Cyanotoxin from algae causes liver failure. Endotoxins from dead bacteria produces pyrogenic reactions. Copper hemolysis, zinc hemolysis, sodium azide, which is a preservative in some of your membranes, causes hypotension. Anemia, bone disease, fever, chills, hemolysis, all these symptoms are associated with water source contaminants. But as you can see from these, it can also be symptoms of other causes, not necessarily water. So the question is, when patients exhibit signs and symptoms, how do you determine and how do you differentiate whether it's water related or something else? And in a typical dialysis setting, in a centralized feed water system, there's a cascading effect with these kind of symptoms. Person nears the water treatment system or where the water first come into the unit would exhibit the system, and then the next, and then the next, and then the next, almost like a domino effect. If you had these occurrences or these symptoms occurring away from the source water and isolated, say, for example, 3 patients in the middle of the pod away from the water and no one else near the water sources exhibiting the symptoms, chances are that it's not a water related problem. Okay, the key is the cascading effect from the source water downstream of that source. Your patients are dominoing effect the same symptoms. Water room environment. This is one of the regulations that is inclusive in the new writing. Water purification and storage systems should be located in a secure area that is readily accessible to authorized users. The location should be chosen with a view to minimizing the length and complexity of the distribution system. Access to the purification system should be restricted to those individuals responsible for monitoring and maintenance of the system. Now, why is access restricted? In this slide, you can see that because every patient in that unit is subjected to one source and receiving that source, it's very easy to have the whole unit affected by a simple act. Take, for example, this headline: Hospital technician wanted to kill as many patients as possible by pouring bleach into the kidney dialysis machine tanks because he was being fired. When they're referring to the kidney dialysis machine tank, that's the water tank, the water holding tank for the RO. So luckily, this one facility discovered it prior to patients being put on. This gentleman was arrested and is now being held in prison and serving. I apologize, but I don't know how long a sentence he's gotten, but it was for attempted murder and burglary. The first component we'll cover is the softener. The softener is a component that is designed to protect the RO equipment and not the patient. RO membranes are very sensitive to buildup of calcium and magnesium, and the buildup of calcium and magnesium reduces the efficiency and volume output of an RO membrane. How a softener operates is under the ion exchange basis. The softener tank has millions and millions of resin beads that have an affinity to cation. And sodium, being a cation, has the weakest bond affinity to that resin. Calcium and magnesium have a stronger bond to that resin. So when the water is introduced into the softener resin, the calcium and magnesium's ability to be attracted to that resin is stronger than the sodium, and the calcium displaces the sodium, and magnesium displaces sodium, and sodium is released in the outflow of the water. So what comes out of the tank is water that's impregnated with sodium. Sodium is readily rejected by the RO membrane and does not allow it to build up on the RO membrane, and that's why a softener is necessary when using an RO system. How a softener works is that, again, for the removal of water, hardness, calcium, and magnesium in exchange. Looking at the right picture with the light blue, you can see that the green is your source water coming in and is and flows through the softener tank, and the uptake tube at the bottom of the tank takes the water that has gone through the resin bed and outflows through the top. The blue is soft water. What occurs at the end of each day is a term called regeneration. There is a finite capability of ion exchange in the water resin or water softener, so that and each day, in order for the water softener to function correctly and liberate sodium, that resin has to be regenerated, or the sodium concentration on that resin has to be regenerated at the end of each day. How regeneration or replacement of that sodium in that resin occurs is, if you look at the left-handed side picture, you have a light green coming out of that smaller tank, which is called the brine tank. This is full of salt. It's a super concentrated or high concentrated sodium solution, or the term used for that is brine. Brine is then introduced at the top inlet of the softener, comes down the tube of that softener instead of going up as normal operation. The brine then flushes the resin with high concentration of sodium or high concentration of brine, and the sheer concentration overwhelms the calcium and magnesium ability to hold on to that resin, and the calcium and magnesium is displaced and is flushed down the somewhat different hue of green. So what ends up at the regeneration is, now you have again a tank full of resin that's impregnated with sodium. And softeners shall be fitted with a mechanism to prevent water containing the high concentrations of sodium chloride used during regeneration from entering the product water line during regeneration, and it shall be interlocked. And it shall be measured at the end of each treatment day. Although the softener is not there to protect the patient, but to protect the equipment, malfunction in the introduction of brine into the RO system can actually have an indirect effect on patient treatment. If brine were to go through the RO membrane, because it is such a high concentration of sodium, the RO membrane is incapable of purifying that much sodium into a usable level of sodium for dialysis. The softener then, the RO system would then go into uh, either interlock or into bypass, and no water will go to the dialysis machine. When no water goes to the dialysis machine, your dialysis machine alarms for no water, and dialysis stops. You won't get any clearance. You can ultrafilter, but your patients are not getting their clearances. And typically, it can take anywhere from maybe 35 to an hour and a half, depending on the size of the system and the type of contamination of sodium into the system. It would take that long to flush out all that sodium back to a level where the RO system can now generate product water that is low enough in sodium content to be used for dialysis. So during that time, your patient is not dialyzing, and hence the indirect impact on your patient. They're not dialyzing for a long time, and shall be measured at each treatment day. This is to verify that the size of the softener that we have can accommodate the full need, full water need, or full ion exchange need for your treatment day. If you were to measure that at the beginning of each day for the hardness, it will always be good because it regenerated the night before. You would know whether or not it can sustain your full day's operation. Checking at the end of each day, it will. Carbon tanks. Carbon tanks, on the other hand, are there to protect both equipment and the patient. Chlorine is still sometimes used as a disinfectant, and chloramines are used as a disinfectant. Chlorine will destroy RO membranes, and carbon tanks can remove the chlorine. Chloramines, on the other hand, can cause hemolysis in our patients, and the carbon tanks remove chloramines. The chloramines cannot be rejected by the RO membrane, therefore, some other method of removing is required, and the most practical and efficient way for us to do that is with the carbon tanks. This is a cartoon of one granule of granulated activated charcoal. Each particle of charcoal has so many nooks and crannies that if you were to take approximately a teaspoon of that charcoal and lay all those nooks and crannies side by side, it will equal the surface area of about 3,280 square feet. If you were to take a football field, which is 100 yards, which is 300 feet, multiply that by 100, which is typically I think is the normal width of a football field. It will equal about almost the size of a football field at 3,280 square feet. So you can see that there's a lot of surface area in a granule of carbon. The requirements are that tanks are sized for empty bed contact time, and the requirement is that it be a 10-minute empty bed contact time for chlorine removal. What empty bed contact time means is that the water, once it enters the tank, must be in contact with the carbon for 10 minutes before it exits the carbon media, hence the empty bed contact time. The calculation is there for anyone interested in knowing how to calculate. And two tanks in series for total empty bed contact time, meaning that one tank is placed ahead of the one tank in a linear fashion. Water goes through the first tank and exits the first tank and goes directly into the second tank. Only one tank is required to adequately or effectively remove the chloramines. The second tank is in place so that if the first tank loses its capacity to remove the contaminant, the chloramine, the second tank is automatically in place to take over that function. So with a 10-minute empty bed, with a total 10-minute empty bed contact time, your two tanks are actually sized 5 minutes, 5 minutes for a total of 10. The requirement is that the carbons be tested 15 minutes after your RO system is in operation. The reason for 15 minutes is that remember the empty bed contact time of 10 minutes exists. So if you were to turn on your RO system and immediately test for chloramine level without waiting more than 10 minutes, what you'll be testing is water that has stagnated in that tank overnight or over the weekend, and it will always give you a false testing. It'll always be negative, or it may be positive, but it won't be an accurate reading. So 15 minutes is 100%, 50% over the empty bed contact time. That should allow enough time for all that stagnant water to be removed before the testing. And of course, the test strip has to be sensitive to the level that you are testing for. And we're testing to a less than or equal to zero point 0.1 is safe for dialysis. Zero point 0.5 is for chlorine. Zero point 0.1 is for chloramine, and that's what we're concentrating on is chloramine. So any testing that you do, your test must be sensitive to the less than or equal to the zero point 0.1 level. Check total chlorine post first tank, and the requirement is before every shift, or if you don't have a shift, every 4 hours. And the pre and post pressure. Carbon can clog, so you can determine clogging of your carbon by sediments with an inlet and outlet pressure. If the inlet and outlet pressure differentiates by more than 10 psi, there's a probability that your tank is clogging. And before every shift and every 4 hours, if you were to test the first tank and it was negative, you can continue dialysis without checking the secondary. If the primary tank was positive and the secondary tank testing is negative, you may continue dialysis, but only within 72 hours. If you cannot change your primary tank within that 72 hours, you cannot continue after 72 hours only on one tank. RO membrane. This is the heart of our purification system, and this definitely protects the patient. It removes organic and inorganic materials. It can remove bacteria, endotoxins, viruses, yeast. It will not go through the membrane. So our product water should be bacteria, endotoxin free, yeast free, fungi free. All those particles or all those items are too large to cross the membrane. Ions, on the other hand, are rejected by it quite readily, except for compounds that are not ionizable, such as chloramines. The membrane itself has the ability to repel ions, such as aluminum, sodium, potassium. That's how it operates, is by repulsion. Product Those items will not cross the membrane, and your product water will be 95 to 99% free of those ion compounds or ion contaminants. Particles are too large to cross the membrane unless you have a structural compromise of the integrity. Then those particles can cross the membrane if the membrane were to rupture. Okay. Monitors and controls. In the case of water quality and conductivity, TDS or resistivity, the remote alarms, the monitor must be visible in both the local site, which is the water treatment room, and the remote site, which is the nursing station. So in the nursing station, you'll find that there is an alarm adjacent to C7. So please take a look at it and see it. If an alarm exists, there's a sign on there that says if an alarm exists for greater than 30 seconds, please notify the technical support or the biomed immediately. V200 includes the means to prevent patient exposure to unsafe product water, such as diversion of the product water to drain, meaning that if we have an alarm situation, it has to be prevented from going to the patient. Now, this can be either automatic or manual, and I'll tell you in the next slide exactly what manual means. And disinfection lockout has to be in place, meaning that if you go into a disinfection mode for the RO system, it has to lock out, feed to the main water system, and your alarm cannot be muted in these situations because obviously we don't want to introduce disinfectant into the water loop while patients are on. Now, when I said manual, this is actually the regulations 5.2.7, a means to prevent patient exposure to unsafe product water, such as diversion of the product water to drain. In the absence of an automatic divert to drain valve for the RO, facility staff must demonstrate knowledge of the requirement to manually stop water flow to the dialysis machine. Now, this can be achieved in one of two ways. Turn the flow off on your dialysis machine or put it, excuse me, put it into bypass. And of course, chemical analysis is required on an annual basis and during installation or when your percent rejection falls below 90%. This is the current requirement for water use for dialysate reprocessing and for production. Bacteria CFU on water is at 200 maximum allowable with an action level of 50. Endotoxins at 2 endotoxin unit with an action level of 1 endotoxin unit. And as you can see, dialysate is exactly the same, 200 with an action level of 50 and maximum endotoxin 2 with an action level of 1 and has to be performed at least monthly. What maximum level means is that beyond that level, a medical director has to indicate what must be done with treatment beyond that level. It's not an automatic stop dialysis. It's actually a medical assessment whether or not you continue dialysis with a report of 200 CFU or greater, because the physician has to assess which is more detrimental, withholding treatment on a patient with a high lab results or subjecting them to dialysis with with a bacterial count of 200, knowing that the ability of the dialyzer membrane is capable of filtering out or blocking that kind of contaminant from reaching the patient's blood. So it's a medical assessment call. It's not an automatic stop dialysis. 50 action level, on the other hand, is if you receive um, levels of 50, greater than 50, but less than 200, you don't have to stop dialysis. You just have to require that you demonstrate an action such as disinfection after the treatment or retesting of the samples to validate and verify that your level is at above 50 and less than 200. Bacterial testing frequency should be performed at minimum once a month for established system, after a suspected pyogenic reaction, after modification to the water treatment system, at least weekly for a new system. And bacteriology of the dialysate is collected during or at the termination of dialysis at or beyond the point where the dialysate leaves the hemodialyzer. And one of the things is because you just have so many machines, it's not very cost effective and cost effective to do every single machine each month. What you're doing is you're doing a random sampling of reflective results of all the machines, because what you're doing with each machine is exactly the same. Is you're feeding it the same water, you're disinfecting it exactly the same at exactly the same frequency. So doing 2 machines per month is reflective of what is the condition of all the other machines. The caveat is here that you rotate those 2 machines that are being sampled so that each machine is analyzed at least once a year. For a home setting, it's every 3 months. For an acute setting, it's just like the chronic setting where it's required on a monthly basis. And again, this is to give you the interpretive guidance or the tag that stipulates that it is the final decision of whether to discontinue dialysis rests with the medical director of a facility. And also, too, that it requires prompt action. Promptly would be met if action is taken within 48 hours of receiving the results of the testing. And these are the typical sites to be sampled. First outlet, last outlet, auxiliary connections like the bicarb feed or the bicarb mixing water, or if you have a granule system, the granule system. If you have a reuse system, the reuse system are auxiliary connections. Chemical analysis, it must be performed at least once per year. And if you have severe seasonal changes, quarterly may be necessary because, again, with season variations, the water quality changes. Whenever substantial changes to the system is occurring, if you're doing major repairs, significant components that's related to purification may alter your production, so it should be tested for chemical analysis at that point. And what again, the new requirement is a percent rejection of water system is decreased to less than 90%, and the sample shall be collected at the end of loop. End of loop because again, if there's work in the piping system ahead of that end of loop, and you were to test it at the beginning of the loop before the repair job has done that has introduced leachable substance, you'd never pick that up if you were to test it before that addition of an unauthorized component. If you were to collect it at the end of the loop, you would notice and discover that event. Again, all your work should be supervised and reviewed for any of those type of incidents happening, but it can happen, and it sometimes does happen where people not familiar with dialysis does work in your system. The end. Thank you.